Hey there, fellas. Right here I have got an engine, and you'll recall that we've done our fair share of engine-related experiments. Now we also have an awesome 3D printer. And you know what we should try making? You can choose from various materials anyway. I suggest we print some crankshaft bearings. Install them and see if the engine can run on them. Let's go. So look here, guys. After removing the bearings, this is the current state of the engine. No oil pan, here we got the conrods, pistons. You can see everything. And this idea occurred to us. We're using the 3D printer for this one anyway. And while we've got this engine cracked open, why don't we try printing some compression rings on that 3D printer? I think we'll be going beyond just engine bearings in this one. On top of them, let's go ahead and make some piston rings. And test all of it at once, let's go. Okay, so we've extracted all of the parts we need. Here we have the crankshaft as well as the bearing. All of that is good and well. These are of the standard size, and check this out. We are going to 3D print them, but out of different materials. We have a few to choose from, and we'll see which is best. If we were to go into the theory, well, there are some interesting things to note here. The actual bearings are not supposed to come into contact with the crankshaft journals, because as we all know, the engine is equipped with an oil pump. It feeds pressurized oil into the engine. And in theory, there's always supposed to be an oil film in between the journals and the bearings. And because of that, I expect 3D printed bearings to work just fine. Quite well, in fact. No, the material might not like high temperature, but we'll find out whether that's true or not as we proceed with the experiment. But what do you guys think? Why don't you pause the video and share your thoughts in the comments? But here we have some samples, we know what size they are, and let's make them already. The printer is quite precise, but assembling an engine requires even more precision than even that. We literally have to get it right to the 100th of a millimeter. As for the printer, different materials are going to have different shrink rates. That means we're going to have to get the thicknesses right through trial and error. We'll keep printing bearings until we get the sizes right. So after grabbing a caliper, the actual bearing, oh yeah, of course I've got a table with the standard sizes. Albeit not all of the sizes are in there, but we've uploaded all of them onto this computer, and we've drawn up a 3D model of the bearing. It's pretty much ready to be uploaded to the printer. This is the thickness we're going for. It looks pretty nice, I think. So after our previous experiments, we're left with 3 types of plastic, namely PLA, PETG, and carbon-filled ABS. We'll be printing the bearings out of these leftovers, and they all have slightly different properties. The PLA is the least temperature resistant, then you have PETG, and the most heat-resistant variety is the ABS. Alright, we've made some prototype bearings. Now we're going to try and install them. Now our first test fit has shown that we need to increase the thickness of these bearings. I think it's all down to them being made out of plastic. For tighter fitment, we need to increase the thickness and do some more test fitting. If everything works out, then we'll properly install them. I feel as if their height might be insufficient. Even if we try test fitting the other half, it still appears as if they're somewhat lacking. Lengthwise, I mean. Nah, you gave it a dab. Now turn it so that it finds its way underneath. You see how it lifts up together with the bearing? Yeah, you're right. The stock one. Not a lot of resistance. Seems too free. I feel as if it has to be tighter. We can't make it any tighter. Take a look at this, though. I mean, terrific, there's a bit of clearance. So far, the clearance appears... I think Slavo might be right. It's just that the material shrinks. Yeah, like all around. Maybe it's because it can't print sharp edges. Instead, they're rounded off. Yeah, and that's what's reducing the radius. I guess we need to... If we had... But then I wouldn't want to have to trim them down. We need to make them slightly thicker. 3/100 is gonna work fine, though. When they're made from aluminum, but these are plastic. That will give us more clearance for oil, though. We've made another bearing, and this one has been slightly extended. The old ones were too short, and they very well could have spun. But now they seem to be flush when I touch them. Nah, man, it's too short. I mean to say it's too long. It will sit flush after a bit of trimming, though. It's not bolted down too tightly, just a slight pinch. Didn't apply too much force. And now there's a bit more resistance at the crank. I mean to say it's where it should be. It's not wobbling around too much. Now we're going to fit some bearings to 3 more journals. And we got lucky. We got the thickness right the first time around. The second time, rather. Because we did have to slightly alter the length. But now we're good. And with that, let's carry on with the experiment. And here we have our lovely bearings. We got different colors. Red, black, blue, gray. And the reason for that is they're all made from different materials. I do think we'll install them all at once. We do want to find out how each of these perform. But overall, I mean, you will notice that they look pretty cool. You got this mishmash of different colors. And so now what you see here is going to be transferred over to the engine. Now, in order to make the piston rings, we're gonna need to... What do we need to make the fucking rings? A 3D printer? We have no idea what we're doing, and so we just drew something out using a ruler. We'll just impose this onto the screen, and there you go. We'll try and get the scale about right. So 17 squares, and take a tiny bit off of the 17th square. 83. Plus the end gap. How do we cut the gap out? Using a box cutter, I suppose? If we use a box cutter and remove the sharp edge, then we should achieve about the size that we need. And we leave a bit of a gap for the ring. From there, all we care about is the thickness of the ring itself. To work out the thickness, we'll use the thickness of the standard piston rings as the baseline. Let me just measure that again. We're aiming for 84.0. Let me just set this to 84.0. Right, so the ring is going to be bigger. After all, we did measure the upper portion of the cylinder. It does taper down as it goes lower. Since we want this to be a tight fit, let me measure this again. But then, no, let's just stick to 3 mil instead. The upper ring has an outer diameter of 83 millimeters, 3.3 mil in width, thickness 1.25. The second ring measurements are the same, except that its thickness is 1.75 mil. Right, so then we keep the ring measurements standard, print them with no end gap and make one using a box cutter, and just stuff them right into the cylinders, together with the pistons. Okay, we've printed out the rings. These will be the oil rings. And these will replace the compression rings. I've got them right here, they're looking good. And from the looks of it, they should work. But then this is an experiment, so you really never know. That being said, we've got some pretty high hopes. Fingers crossed that they actually work. I mean, rubber piston rings worked fine, and so should these, right? But why don't you guys go ahead and pause this video and tell us what you think? Your comments would be a very interesting read. One, two, three, enunciation, come to me. Now, to make sure we got the bearing thicknesses right, we need to measure the clearance between them and the crankshaft. We'll do that with the help of a plastic gauge tool, and yeah, let's do it. Yeah, let's do it. What the f*** are you even saying? And with the help of this simple method, we've worked out the clearances. We are looking at 0.075, while the limit for this motor is 0.15. From the looks of it, the clearances are well within range. Okay, we've printed out the rings, they're looking good, but there is one caveat. Rings 1 and 2 are good when it comes to their thickness. That's all good and well. While ring number 3, which is slightly thicker, seems to be sitting a bit too tightly. As a result, we have to rub them down with some sandpaper to make them a better fit. Alright, so check this out. Our engine, which we've fitted some plastic rings as well as some plastic bearings to. I mean, it's not half, but a certain portion of the internals is now about to be subject to some testing. It is ready and assembled. Let's go fit it to a car. The engine with an assortment of plastic parts is back together, and now the interesting part, which is starting it. Oh wow, it's even cranking. Great, it started. Goodbye. Nah, I'm kidding. In all seriousness, this is great. Even with plastic rings, it was still able to run. As for why we shut it off so quick, that's because there is no coolant in there. No water or any other liquid inside the cooling system. And something we'd prefer to avoid is the cylinder wall overheating, and the rings that are made out of plastic, well, best case scenario they stick. Worst case, they just melt altogether. And so we're going to pour in some coolant and then conduct a proper startup. You see that? Wait, let me try that one more time. Here we go! Oh, wrong way. It drives. Who said it won't drive with plastic rings? Did you expect it to run? I thought it wouldn't start at all. Don't know where the temperature is at, but it's running. Can you turn the AC off? No, I can't turn the AC off, sadly. Okay, there's smoke coming out from the breather. Or where's that coming from? Oh, that's the exhaust? Why does it reek of plastic? He's sort of doing a burnout. Doesn't seem like it's going to get far. To that end of the complex. Doesn't want to pull anymore. To that end of our building. Oh, the turn signal is blinking. What, you want to go left? Okay. It's fucked. What's the matter? Where's it coming from? It can't be. Looks like there's no compression. Compression is gone. Maybe the plugs are clogged? Now we have to push you all the way back? I'll just use the starter motor. It drives alright, even though it is jerking around. Drives alright, he says. Something's gone wrong. Didn't make it far, unsurprisingly. Plastic rings do not work. Well, they work, but not for long. Isn't the video about bearings? Bearings? We also fitted some rings. Anyway, we'll investigate, see what happened to them. I'd imagine all of the rings have melted away. Are you trying to say the bearings are all gone? Do you hear that noise? I do. It's not that they're gone, they've just been crushed. I can see evidence of worn metal parts, when you should be seeing plastic. Look at how dark it is. Did it run for a minute at least? A bit longer? Yeah, I think so too. 5 maybe, or a bit less. My flashlight isn't great though. Shut the front door! Seriously? My goodness. Oh my. We'll put them in the unfit category. They are cooked. So look here, guys. We've taken this engine apart, and this is what we're looking at. I mean, yeah. Whoever wrote that this isn't going to work, you were absolutely correct. I mean, it sort of almost did. You see, here's the thing. The main bearings... Yeah. The bearings that were underneath the caps which were under the most load, all of them have been destroyed, crushed, some of them broken. This one looks especially horrifying. I guess it melted, but then I'd say it was split apart. On this end, we have one that cracked. Split into two pieces, didn't melt though. And it didn't even really get crushed. It's a pretty clear picture. The rod bearings, well, these are properly they're screwed. Same story with these, they're all tattered. Crushed, overheated. Just look at how these were getting crushed, to the point of spreading apart. None of them survived except for... Look at this. The gray bearings are intact. This is the carbon fiber reinforced ABS. They're quite durable, and so the only plastic that survived was this one. You gotta hand it to this variety, because, I mean, it is very much still intact. Looks alright. As for the plastic piston rings, these just look wonderful now, don't they? I mean, from the looks of it, some of these, like... The upper ring has been melted by the heat and spread around the piston. I mean, obviously at those temperatures. In some cases, gases were blowing by. And on a few of these, two to be exact, you've got the rings missing about half the way around the pistons. I'd imagine they overheated and even burned up, because we saw a ton of smoke coming out from the breather. That tells us something was burning inside the engine. It must have been this lovely plastic, which was burning up and puffing. All of that soot also made the oil go dark. On this piston, you also see more than half of the rings missing. You can see that they burned up and melted, and yeah, that's what happened to them. This rendered the engine pretty much incapable of operating, because, well, check out this lovely picture right here. This is the oil pickup, and look at the chunks sticking out of it. That there is what's left of the bearings. Maybe even pieces of the rings have found their way down here. The point is that plastic is a great thing, but useless for this sort of application. And so replacing metal bearings with something made from plastic, well, as you can see, it just didn't work. Same goes for piston rings. And that's the experiment. Whoever wrote that this wouldn't work, good on you. Whoever said this would work, even better on you. And that's all I got for you. Watch us, subscribe, and catch you later.